This video is on giving objects an electric charge. First, let's talk about charging insulators by contact. If we rub two different materials together, they will tend to acquire equal and opposite charges. And the reason for that is that these different materials have different affinities, or we might say desires, for electrons. This is sometimes called charging by friction because we need to use friction through the contact in order to make that happen. If we have an object that's already charged, we can charge an insulator with it, but we have to touch the insulator at several points with our already charged object to achieve any kind of uniform charge distribution. And why is that? Well, that's because charge doesn't travel through an insulator. It stays pretty much where you put it. So if you want that charge to be distributed throughout on the surface, then you need to touch this object with your charged object at several different points. Now let's deal with charging conductors by conduction. If we touch a neutral conductor with a charged one, what happens? Well, the formerly neutral one becomes charged, and it will have the same charge as the charger. Do we need to touch the previously neutral conductor in several different places? You remember this is what we had to do when we were charging an insulator. And the answer here, though, is no. And that's because conductors have mobile, or sometimes we call them conduction electrons. And so the excess charge will disperse through that object. And this is a topic for another day. It stays on the conductor's surface. To summarize so far, when we put a charge on an insulator, the charge stays where we put it. And when we put a charge on a conductor, the charge spreads across the surface. Now, another type of charging is charging by induction. And if we're charging a conductor by induction, what that means is we end up with a conductor being charged without us ever having actually touched it with a charged object. And you might think, how is that even possible to charge something without touching it with something else that's charged? Why don't we show you how that's possible? Suppose we have two neutral conductors atop insulating stands, as we see here. So we have metal spheres, and these stands perhaps are made out of plastic. By not drawing charges on these spheres, we convey the message of neutrality. You've learned previously that all matter is composed of protons and electrons, and those are positively and negatively charged, respectively. And so there are lots of those here, but by not showing any of them, we show that all of that charge is uniformly distributed with no buildup of charge in any one place or another. In part B, we're going to bring a positively charged rod close to these spheres. And what's going to happen is the conduction electrons, some of them anyway, are going to tend to move towards this positive charge because they're attracted. Now, what that's going to do here, these positive charges haven't moved. They have just been uncovered by electrons that have moved. You should have learned in chemistry that the nucleus of an atom, the protons, they don't really move around too much. It's the electrons that do the moving. That's what's happened here, but it has uncovered these protons on this side. What has moved are the negative electrons towards this positive rod. Now what we're going to do is we push the rightmost sphere away, touching only the insulating stand. If we have that rod there, and once again, these negative charges are attracted, and these positives have been previously uncovered, look what's happened. Now, when we move the rod away, these negative charges are going to disperse on the surface, and these positive charges, again, the positive charges won't move. It'll be the electrons over here that will move, but we will get an effect such that all of these positive charges are uniformly distributed. And you can see that we have charged both of these objects, but we have not touched either of them with a charged object. That's the definition of charging by induction. Here again, we have a conducting sphere that's atop an insulating stand. And let's label the insulator here. The stand is made out of plastic or glass or something like that. And then we have a conducting metal sphere on top. Again, we're not going to draw any charges. That indicates that we have a neutral situation. Now we're going to bring a negatively charged wand close, but not touching. Well, now these conduction electrons, some of them anyway, are going to run away from that negative rod, and that will have uncovered some of these positive protons which haven't moved on this side. Is there now a net force between the wand and the sphere? And that answer is yes, and it's attractive. Closeness wins, according to Coulomb's law, which is a topic that we'll cover later. But you have an appreciation of this idea already because you've probably worked in your day with magnets, and you know that the strength of a magnet is stronger when it's closer to the iron object, let's say. And that's what we have here. These positive charges are closer to these negatives, and there's an attractive force there. These negatives are further away. That is a repulsive force, but it's a weaker repulsive force because the distance is greater. So the attractive force wins. So there is a net force between the wand and the sphere. Then we're going to connect this sphere to what we call ground with a grounding wire. Let's redraw what we had previously. Let's put those kind of like so. And now we're going to draw in a grounding wire. This is the symbol for ground here, and we are connecting a wire here. We could use our finger actually to do that, but here let's just use a grounding wire. And let's indicate what type of charges are going to be flowing through this wire. Well, these negative charges, they can move, and they are going to be repelled, aren't they, by this negative rod over here. So those electrons, some of them are moving down that way. Now we're going to disconnect the wire. Let's redraw the grounding wire without any charges on it, and we're going to show that it's disconnected now. And what has happened? Well, what's happened is some of the negatives that were on the sphere have gone to ground. They've left. And so, in effect, we end up with a net positive on this sphere. And those positives are directed a little bit to the right there because they're still attracted to this wand. And now, when we remove the wand, the net positive charge spreads out uniformly like so. Let's end this by stating what happens with charged particles within the sphere that resulted in the net charge distribution on the sphere changing from figure 4 to figure 5. And we've said this several times already, but here it is again. The positive charges actually stayed in place, but the negatives that remained on the sphere spread out evenly, which covered or canceled some positives on the right and exposed some positives on the left.